here we have the title of the talk. And I just wanted to mention quickly in the beginning that I have 2 papers that were accepted for publication in the International Journal of Astronomy and Astrophysics. They're coming out next month. They're cosmology papers. One on the left are actually coming in the same issue. They go together. First one basically puts the nails in the coffin of the Big Bang. Pretty much I compared to Big Bang to stationary universe tired light model on 8 different tests, and find that on all 8 tests the static universe tired light model fits the data better. And then I offer an alternative to the Big Bang in that paper of continuous creation. And in the second paper, it goes on to talk about the existence of a negative Hubble constant, so to speak, non-velocity Hubble constant, where you have blue shifting, continuous blue shifting of the spectra of light passing through galactic clusters, any large gravity wells in space, like superclusters, gravity clusters. And that's something not explained in current physics, but it's a prediction of the subquantum kinetics physics, which I've developed. And so those are coming out. And by the way, I think Brendan may have mentioned to you, he's working on simulating Model G of subquantum kinetics, which simulating particle structures like neutron, subatomic particles. And here's another thing that's just coming out next month. It's the Origin of Gravity from First Principles book. And I've written in chapter 7, the origin of gravity and its effects according to subquantum kinetics paradigm. And that presents in subquantum kinetics, the gravitation plays a broader role than it does in general relativity. And it sort of, general relativity emerges as a correlated, all the effects that it predicts emerges as a corollary, but there's in addition to these other effects, which are very interesting. So to get started with the talk, this is my, I have 2 websites. The Sphinx Stargate, which is etheric.com, and starburstfound.org, it's the Starburst Foundation website. A lot of my papers you'll find as free downloads on Starburst, in the archive, and my books and videos that I'm selling, you can purchase those through etheric.com bookstore. So to summarize, sorry, there's various types of cosmic catastrophes that have been proposed. I'm proposing galactic superwave. There's also large magnitude solar flares, comet or asteroid impacts, or encounter with a dense interstellar cloud like Fred Hoyle once proposed, or nearby supernova explosion. And of all these, the galactic superwave phenomenon occurs most frequently and is can be among the most devastating. And it's tied in with large magnitude solar flares that influences the sun when you have large events. So this is work I did for my PhD at Portland State University. I was not in an astronomy program. I was in a system science program, which was interdisciplinary. And the idea that the evidence for testing the hypothesis came from many different fields, not just intergalactic astronomy and galactic, but also solar system astronomy, cosmic ray astronomy and the Earth looking at the polar ice records, paleontology, geology, climatology. So there was a lot of fields I had to study. It's sort of like doing Sherlock Holmes work on an event that happened in the past, and you find the evidence in different places. It was quite a long dissertation. It was the longest in the history of the program, which they pull out to show people, to, I guess, make them think they have to do the same. But this is my book, Earth Under Fire, which summarized conclusions of my dissertation. It's more for a lay readership. First published in '97 and then reprinted in 2005. And you can find it on my website. Also, I have a CD disc of my dissertation, which is updated with recent newer findings I put in places in the dissertation and noted the new additions. Also had published a paper in Earth, Moon, and Planets Journal in '87, giving the basics of the idea of the galactic superwave theory. And a lot has happened since then. So how many years is that? 35 years almost. And it's in time for doing an update publication, and that's on my list of things I have to do. So much has come out to confirm the hypothesis since that time, and I had quite a bit of evidence at that time. So it's '87. Also, here's a video that was made based on my book, Earth Under Fire. It's a very, very nice video. You can find it on the Gaia TV platform. They have many videos. You have to subscribe. I understand they give you a month free or something. And so if you just search for that title, you can find it. It's about 40-minute video. So my journey, well, you might wonder where I got the idea to research this, how I formed my hypothesis. It was based on the discovery of a time capsule message written in zodiac lore, the star lore. So it's basically under the field of archaeoastronomy. And here's a quote from Oral Scott, who's a star lore mythologist or writer about star lore, myth, in fact. Says it's been suggested that perhaps a patriarch of the ancient world wishing to preserve posterity perishable record of some great event or crisis chose this means of doing so, and by his arrangement of star groups wrote in the sky a message that would endure forever. And I believe I stumbled on this message, and it basically informed me about the galactic core, that there was an outburst around 16,000 years ago. And this was something that you didn't find in the astronomical literature. So at that point, I felt this was very important. It would have such a major effect on the Earth. It changed my PhD dissertation topic and chose this, which I thought was more important at the time. So I didn't base the dissertation on the astronomy findings, besides the dean wouldn't have approved. It was all based on testing a hypothesis based on observations out there. So I just mentioned that it deals with galactic core explosions, and that they found that 1 out of 6 spiral galaxies have active cores, which means that a galaxy like our own would spend about 17% of its time in an active state, the other 83% in a quiescent state like we observe it currently. And it appears that during the entire interglacial, it's been in a quiescent state. When it goes active, when a spiral galaxy goes active, it appears, its actual appearance changes, and it would be classified either as a Seyfert galaxy, an N galaxy, or a quasar in the very luminous cases. Here's a picture of a Seyfert galaxy. Here's another Seyfert. The centers are very bright, and they have a bluish white light, which is of synchrotron origin. It's from the cosmic rays the core is putting out. And as they get decelerated in the magnetic fields, they generate synchrotron radiation, which they beam outward radially. And in some cases, the core can get so bright that it masks the whole galaxy. It's like in a quasar. For a long time, they didn't know there were galaxies until they got the Hubble telescope up and they began seeing that these quasars were really active cores in the center of the host galaxy. So here's the center of our own galaxy, Sagittarius A star. This is an X-ray image, and it's pointing out where it's located there. Based on they've done observations with ALMA project in microwaves to try to detect the size of the emission region. And what they found is that it's actually, the emission region is smaller in size than the Schwarzschild event horizon, gravitationally lensed Schwarzschild event horizon. If you would assume that Sagittarius A star is a black hole, which would tend to refute the black hole model, because we're not supposed to see any energy coming out from within a black hole. Here I show the blue dot is about the estimated size that I estimate for the size of Sagittarius A star. It has a diameter to it. It's not a singularity, in my opinion. The way the scientists explained that, astronomers suggested that maybe we were seeing emission on the outer surface of the black hole. And so the problem with that is that if that was the case, we should see it rotating, because everything around Sagittarius A star is orbiting very rapidly. And they observed this for a long time, and this has not changed its position. It's stayed right on. So I don't know of anybody else, but I call into question the black hole model based on this. I haven't seen anybody else calling attention to this in that manner. In my book, Subquantum Kinetics, it's a physics theory I developed beginning 35 years ago or more. Well, I've been working on it for over 40 years. It was published in 1985. It's in this physics approach, black holes cannot exist for the purpose that, one, it being that gravity field inside particles doesn't go to singularity. It sort of plateaus off. So if matter were crushed to very high density, your force pulling the matter together would diminish as the particles approach each other. So they would not be able to form a black hole. And the other is a prediction that comes out of this, which predicts that photons should blue shift in gravity wells, very strong gravity wells. And so you end up generating energy actually in the core, and it opposes the collapse and actually brings it to a halt. So you end up having basically a very luminous, hypermassive star that's generating both matter and energy. Now, you don't have to accept that for the superwave theory. You can treat the galactic core as a black box. But I just thought I'd mention I have a different perspective on the core. and which is other astronomers have proposed cores like Sir James Jeans, Houghton Arp, Sarasik and Britsumian have all proposed that cores are places where energy conservation may be violated and things are coming into being there. So here's my derivation of statistics about the galactic core, its mass, which is accepted around 4 million solar masses. I have determined the radius is around 21 solar radii, and plus or minus, not exactly that, but would have an average density about 600 times that of the sun. So it's about a mildly dense white dwarf. White dwarfs most of them would be actually more dense than that. Puts out about 2.5 billion solar luminosities in its current quiescent state. Surface temperature would be about 70,000 degrees. So it's radiating the X-ray region. So it would be in a way black to optical visibility. Average internal temperature about 18 million degrees. Would have a matter creation rate of about 5 solar masses per century. Mass loss rate of about 2.5 solar masses per century. So you could say the difference, about 2.5 solar masses, would go into increasing the mass of the core over time. So it would actually grow in mass until it would have a galactic outburst, galactic core explosive event, and it would tend to eject a lot of its mass at that time. So this is a graph showing how the radio luminosity of our core compares with those of active galaxies on a logarithmic scale. And in my thesis, I proposed that during the active period, the core had jumped in luminosity, radio luminosity, by about over 5 orders of magnitude, 3 times 10 to the 5th. So it would have appeared like similar to a Seyfert galaxy. Giant elliptical radio galaxies would be even more powerful, and Seyfert radio galaxies can be putting out even more radio luminosity. So our core, in my opinion, hasn't been among the most luminous during its active periods, which is good from our standpoint, because it could have wiped out, if we had a quasar event, could have wiped out life even at this distance away. If you want to locate the center of the galaxy, it's between Sagittarius and Scorpio. I put a ring there to indicate the proximate location. There is a myth in ancient Greek lore that says that Sagittarius aims his arrow at the heart of the scorpion. So if you make a sighting there, you come very close to the location. But the arrow is not currently pointed properly. You have to regress it back in time. It turns out that Gamma Sagittarius has the highest proper motion of all the stars in Sagittarius. It's a very nice pointer star. So it almost acts like a chronometer. And if you go back in time, you see it was pointed accurately about 16,000 years ago. And I took that as an approximate date for my thesis. So here's radio observations that were done of the galactic center, showing that there's a lot of radio emission around the center from dust and ionized clouds, non-thermal, so a lot of magnetic fields there trapping cosmic rays. So when you have a galactic core outburst, in my theory, I was proposing a number of points to the superwave hypothesis. First, that the cosmic rays from the outburst travel radially outward in all directions isotropically. they're not confined to just a jet, like has been the standard idea that has been, you hear a lot. In this theory, they're isotropic, and they're confined in a shell, so to speak, of it, which is the duration, basically the duration of the outburst, and they're traveling close to the speed of light. And they penetrate through the galactic medium and are able to reach the solar system and beyond. In other words, they can penetrate through the entire galaxy. So,
Hey there, Paul. Paul, is it possible to speak a little bit louder? Because it's quite difficult to hear.
oh, somebody you should have said earlier. Yeah, my voice is not working today. So, is this better? Can you hear me better now? Or?
That's a bit better, yeah.
Okay. Did you miss anything I'd said that you wanted me to repeat? Okay, okay. So this is what I suggested, my sketch of the way the magnetic fields are in the galactic disk, that there's not only a transverse component, which is easily visible in astronomical studies. They see the grains aligned by the magnetic field, and that's showing up the transverse component. The radial component is more difficult to discern. And I'm proposing that it penetrates through the transverse component so that a volley of cosmic rays would not be stopped by the galactic magnetic field. And in fact, if you look at the energies involved in these outbursts, they greatly exceed the energy density of the magnetic field in the galaxy. So basically, the magnetic field is like putty in the hands of the galactic core explosion. It aligns to the way the cosmic rays would be going. When the explosion occurs, you get both cosmic ray protons and electrons in equal proportions released at the core. But because the cosmic ray protons are 2,000 times more massive, they would be traveling slower. In other words, they'd have lower Lorentz factors. This shows the Lorentz factors, particle kinetic energy. So electrons, you're going up to 1,000 or more Lorentz factor. And so most of the electrons, even the low energy ones are well over 1. So yeah, they're basically traveling at the speed of light, or 99% the speed of light, 99.9%, 0.999. Whereas the protons, they have a big hump that's subrelativistic. And they end up getting weeded out, so to speak, by the magnetic fields in the galaxy because they're going slower, and their velocity depends on their Lorentz factor, and they have quite a spread of Lorentz factors. Their blast, the volley will not remain as a coherent shell with the protons. They sort of spread out, and then they're susceptible to the magnetic fields, which sort of corral them. They get trapped in the magnetic fields. But the electrons don't. They stay together and they proceed outward. And what we see in exploding galaxies are mainly the electrons. We don't see much of the effect of the protons because electrons are able to produce the synchrotron radiation that we see. But you assume that the protons are there, at least in the beginning. So at the very high energy proton end, you would get protons accompanying the electrons, the very high end of their spectrum. But after a few weeks or months of the superwave, the proton percentage would decline enormously, and it would be mainly electrons So the electrons are going so fast, being hyperrelativistic, that their synchrotron radiation, due to their interaction with the magnetic field, would not be emitted perpendicular to their direction of travel, but instead in the forward direction in a narrow cone angle. And this effect is called relativistic beaming. So when you're looking at the bluish core of an active galaxy, you're seeing synchrotron radiation is being beamed radially towards you as those particles are traveling radially outward. Now here's some recent news releases that were made that support the superwave hypothesis. This is from 2015. And you see, a lot of this evidence had to wait, new telescopes being put up in space, because at the time I made my proposal in '83, we didn't have any of this stuff. Not even the Hubble telescope was up yet. Here's Galaxy PDS 456, and they studied it with the NuSTAR, Nuclear Spectroscopic Telescope Array, which was in operation since June 2000 something, sort of cut off there, 2015 or 14. Can I move this around? Let's see. Yeah, okay. Since 2012. And it's the European Space Agency's telescope. And they found extremely high velocity wind moving radially outward, isotropically away from the galaxy's center in all directions at up to 30% the speed of light. So prior to this, they had assumed, astronomers and general established view had been that the winds produced by active cores issue primarily from their poles in the form of jets. So this started to change that view. Let's see. Then there's this. Now, this was just 2 years ago. After 37 years from the time my dissertation was published, they made observations with Hubble telescope camera that further validated superwave theory. Astronomers led by Arav, physics professor at Virginia Tech, discovered energetic outflows most powerful ever witnessed in the universe. Looking at the far ultraviolet data from the Hubble telescope, cosmic origin spectrograph COS, they found that active galactic nuclei were producing immense high-speed outflows of highly ionized gas, which in one galaxy was traveling at as fast as 7% the speed of light. Now, this is just the gas. These are not the cosmic rays. So this is what the cosmic rays are propelling. And over a span of 5 years that they studied this, they found the outflow was accelerated by 0.5% of the speed of light, as if it's being driven to higher and higher velocities by the energetic cosmic ray blast from the quasar. So this is a quasar. It's a more powerful outburst than what I'm proposing for our galaxy, but the same effect you would see dust and gas being pushed outwards by the superwave. It says also they unexpectedly found that these high velocity flows penetrate substantial distances through a galaxy, as much as 5,000 light years. So that was supporting another major prediction of the superwave theory. And in one case, almost 10,000 light years through the galaxy. Okay. Now, at the time I published my dissertation, there was some extragalactic evidence indicating this isotropic expulsion of cosmic rays. And this is an example shell structures seen around a galaxy with an active nucleus. And the only way you can reason that there would be shells is that there's some isotropic cosmic ray volley coming out from the center that would compress the gas in this fashion. And then there's what's called the ring galaxies. And it's quite, this is a category of galaxy, actually. A certain category of galaxies look like rings. In other words, the volley, as it cosmic ray volley comes outward, it compresses the gas in the equatorial plane into a ring, which the ring being in the plane of the galaxies, in the equatorial plane of the galaxy. And here in the left, you see actually two rings, and the right, a single ring. And here's another one on the left. And the one on the right almost looks like Saturn. Again, that's a galaxy, actually. Here's a picture of a Andromeda galaxy. These black dots chart the emission nebulae in Andromeda galaxy. They're being energized by probably cosmic rays, and something has caused them to form this ring. And again, you come to mind the idea of a isotropic outburst causing them to develop this ring feature. Also, in my dissertation, I mentioned about Lin and Shu's density wave theory of spiral arm formation, which could explain why spiral arms remain extended in spite of their differential stellar orbits. And in my dissertation, I proposed that hydromagnetic shock waves formed in the spiral arm disk by radially propagating superwave cosmic rays could be the driving force for Lin and Shu's density waves. Now, of course, then there's Milgram's theory, the MOND. You've all heard of MOND, modified Newtonian dynamics. And he's proposing that you don't need dark matter, that if you assume that the galactic gravitational field falls off faster than inverse square. And actually that is a prediction of subquantum kinetics. So I've had an interest in Milgram's theory, that because a lot of people have done studies and shown that if you adopt that kind of gravitational fall-off, potential fall-off, that you don't need dark matter in spiral galaxies. So the same evidence that supports his theory also supports the proposal or the prediction of subquantum kinetics on that matter. Milgram's theory was probably just starting to be published in '83, and that's why I didn't mention it in my dissertation. This is a sort of representation of a superwave. This is from the video Earth Under Fire, sort of an artist depiction of what it might look like. Now, there's both the present location of the superwave and the apparent location. So if, let's say, we had a superwave that took off around 14,000 years ago, was an outburst 14,000, let's say. These cosmic rays are traveling outward at the speed of light. And let's say they interact with the medium somewhere. They cause some radio emission in the galactic equator. And the light radiation from that emission they cause would then come at the speed of light back towards us. So if E represents Earth and GC the galactic center, this is like the two foci of an ellipse. So that in effect, we would see the evidence of the superwave in an elliptical horizon, or in effect, an ellipsoid, prolate ellipsoid. But in actuality, the instantaneous position of the cosmic rays would be along this circular horizon or spherical horizon out here. I guess I assume that's clear to everyone. Okay. So this figures quite interestingly here when you look at the map of the galactic non-thermal radio background radiation, which you're all familiar with. And they believe that this background radiation is produced by synchrotron cosmic rays. And in the past, it had been proposed, well, maybe supernova explosions are supplying this. You know, this is a big question, where do these come from? Because you see them also at high latitudes. You see this radiation not only along the equator, but also at high latitudes. So what I did, I took this temperature graph. They published a temperature graph of the non-thermal background along the equator, and it looks like this outer irregular curve here is the actual observed temperature of the non-thermal background. The best alternative theory was this, to predict it. Here's the superwave hypothesis prediction. And the reason is because that ellipsoid there, you see the cosmic rays here are much closer to the galactic center, and so more powerful. They're producing more powerful radiation effects there than the ones further out at other angles coming out. So that's why you would get the skewed graph in it. So it makes a very nice fit. And then later, when they got the gamma ray telescope up, they began seeing this diffuse gamma ray background radiation, which they had a hard time explaining because it would require continuous source of cosmic ray electrons at high latitudes. And the question is, where were they coming from? And the superwave theory proposes that's the superwave, is evidence of the superwave, which not only you see the evidence at along the galactic equator, but also at high latitudes too. Here's a map of the gamma ray background. And you see in this region of faint enhancement along the axis from the core. And some astronomers did computer photoshopping or whatever to enhance that, and ended up with this called the gamma ray bubbles, they call them. I guess you've already heard about these. But the important thing is to realize that these are accompany emission all around them here. It's just they're more enhanced in this region. And it's probably because the cosmic rays are able to travel more unimpeded outward along the pole region. If you have this model, so you see the galactic magnetic field here tends to combine them. So these have more impediment than these. So, so you get more progress. You see more extension along the axis as a result. And if you do some measurements, if you make the assumption that these were traveling close to the speed of light, and it took speed of light for the results of them to reach Earth, you end up coming to around 36,000 light years plus 27. Well, it ends up being, do the math on the trigonometry, comes to around 40,000 years. And it's very interesting that one of the most powerful galactic core explosions that we've had in the last 100,000 years happened at that time. And I'll show you the evidence for that. So, but that came out after my dissertation. Now, this is from my dissertation as evidence for the superwave theory. This is a map of looking down on the galactic plane with the Earth, the polar coordinate map here, and the galactic center up here. Oops. And what I'm plotting here are young supernova remnants with the idea that I hypothesized that the superwave was actually triggering supernova explosions as it went out. So if you had a star that was close to unstable, the superwave would come by, maybe make a gravitational disturbance of the star or push some dust into it and push it over its unstable level and cause it to explode. And what I found was of the supernova that we know their positions accurately, which are the ones close to us, they all lined up in this band between around 12,500, 16,000 years ago, which is the range time I was proposing you had a superwave. These others could be lining up, like here's one, but we just don't know their positions accurately enough. There's also the Vela supernova remnant, which is here. It's the closest young supernova remnant to us, relatively young. It was detonated around 12, 13,000 years ago. And the interesting thing, if you look at the time it takes from the time, suppose a superwave was passing the Earth and triggered Vela at that time, continued at the speed of light, and then triggered the Crab Nebula supernova. And then the light eventually reached us. It turns out that same event horizon appears to have triggered both the Vela and the Crab remnants, explosions. So this I suggest is evidence that the superwave is a relativistic phenomenon. It travels essentially the speed of light through our galaxy. Also, a lot of this information you also find in my book, Decoding the Message of the Pulsars. By the way, both Vela and Crab are marked by the two most unusual supernova, the two most unusual pulsars in the galaxy, almost as if somebody wanted to call our attention to them. That book is a book I've written on extraterrestrial communication, and it's it's pretty much above the standard lay reader in some ways, but it should be able to be handled by people with astronomy background quite well. I just want to show, here's the Vela pulsar. Here's where it was about the time of the Vela explosion, knowing its current rate of velocity and direction. Here's where it is today. This is an image showing the direction it's going. Now here's the Vela explosion site. So it shows it didn't originate from the supernova explosion, but it is placed there sort of as a marker, it seems. And that's a very interesting thing. Here's the Crab. Crab is the most luminous supernova remnant in our galaxy, at least brightest to us, because it's so close. And it's in the galactic anticenter, actually between the horns of the Taurus. And the anticenter is located just a few degrees further over. So in this region, the cosmic rays would be traveling away from us into the remnant. And so all the, by the way, supernova remnants will trap the cosmic rays, produce a lot of synchrotron radiation and ionization. So they're not able to penetrate through a supernova remnant because of its ionized plasma. It's very turbulent. And So they sort of light up like neon signs. And so they're kind of probes of what the superwave is doing. And you see a lot of activity around the pulsar. The pulsar is somewhere around here, and you see a lot of luminous activity. In my thesis, I made the proposal that the pulsar is actually not located at the core of the supernova explosion. It's actually traveling at the forefront of the shell. And we do see some supernovas that have ejected the core, the neutron star, from the center, and is actually traveling outward ahead of the supernova remnant shell. I believe that's the case for the crab remnant. It's just we can't see. It's difficult to make that determination. But some various things that it does, you can conclude that seems to be what might be going on. So when we see this, they call them wisp activity. They're luminous wisps that appear and they propagate away from the pulsar. And I'm proposing that's not due to the pulsar's wind, but to the superwave wind that's striking the shell around the pulsar. And pulsar might have a magnetic shell of ionized material around it that deflects the incoming superwave cosmic rays and causes these luminous effects. We can see this more easily in the case of the Cassiopeia A remnant. You remember back here, Cassiopeia A is located here instead of here. So we have a sort of side view. So because cosmic rays coming this way and we're viewing this way. And so we could see if they're coming asymmetrically. In fact, they are. Here's the direction the superwave would be going. This is an X-ray image, and you see it's much more luminous on the upwind side, the side facing the galactic center. So, there's a question is what's energizing this? And is the astronomers that published this, they didn't know about the superwave, and they were trying to figure out what could be causing this X-ray radiation, which was a puzzle to them. This was a news release back in 2011. A quasar turned on. At first, they thought it was a gamma ray burst, and the problem was it didn't subside. Just a minute. Just turn it off. Sorry. Maybe my wife can help me to get this thing turned off. I'm having trouble. Okay, there we go. There we go. Okay. So it ended up continuing, and you see here's a graph that shows even at 9 months, it was luminous. But the important thing to see is that in the first 3 days, it was the most luminous. It was almost 2 orders of magnitude more luminous than afterwards. So this is the first time we've seen a quasar or any kind of active core turn on. And so this is valuable information. And if we can extrapolate from this situation, we can conclude that maybe the worst of a superwave would be in the first 3 days. And it might die down after 3 days. But that's just a hypothesis. It's advisable staying inside, not go out for the first 3 days at least. So here are various effects that I had proposed to be associated with superwave. It could have a gravity wave effect. This would be longitudinal, not transverse, not a quadrupole gravity wave, but a longitudinal scalar wave type gravity wave. which could cause earthquakes when it would strike the Earth. A polar axis jerk could affect the spin axis of the Earth, cause a nodding effect or a jerking to the axis. Also, cosmic rays the background would elevate the terrestrial background and cause the rate of genetic mutation to increase. So I'm suggesting stay indoors for the first 3 days at least. It could partially destroy the ozone layer, increase the amount of UV radiation. The cosmic rays and the EMP would destroy satellites. Communication systems would be down. It'd be similar to a Carrington event that they proposed all these for a solar flare event. All these things could happen. Maybe your shortwave radios would still function. Power lines could be damaged, develop voltage surges, burning out transformers. So grid power could be down for up to 10 years. Good idea to have a solar installation or free energy if you can get free energy. Then the cosmic rays, the effect would be to cause a temporary climatic cooling. And that's just due to the increased cloud cover, because cosmic rays, as they strike the atmosphere, produce ions, which would be like condensation nuclei, which form clouds. So that could actually, as the bombardment continues, the cloud cover would continue and it would cause actually climatic cooling just from that. Also, it would tend to darken the stars. It would bring, if it persisted long enough over months, it would bring cosmic dust into the solar system from outside the solar system, because currently the solar wind keeps our solar system clean of all that stuff. It sweeps out all the dust, and most of it anyway. We still have stuff coming in, interstellar dust still they find coming in, but during one of these events, the superwave in effect overpowers the solar wind, and the boundary, the Iliopause boundary, would get pushed in well past inward, even closer than the orbit of Mars. So all this dust is going to be coming in and make weird illuminations in the galaxy. So people who witnessed this in the past, they would have seen strange shapes. And maybe where our myths about Halloween came from, about the strange things happening in the sky. If we did have a cosmic dust invasion, if it was a long event, because not all are prolonged events, so we see evidence that a lot of these can be just a year long, maybe even. But if they last for months, then that's when the cosmic dust starts invading and could initiate either global climatic warming, or which would, well, in both cases, there would be a climatic warming effect, a net climatic warming. And with climatic warming, it can go both ways. It can either create an ice age or terminate an ice age. It's counterintuitive that would create an ice age, but the idea is that it evaporates a lot of water, and you get a lot of humidity in the atmosphere, which ends up creating a lot of snowfall in the northern areas, and a lot of snow accumulation, eventually glacier formation. And in the case where you already have ice sheets, it can initiate actual melting of the ice sheets. Another thing, it would form a cocoon around the sun. So the dust would form a cocoon. So that it would change the spectrum of the sun. You tend to have more solar infrared. And I did a study in my dissertation how this would affect climate. And that would tend to create a warming effect, because infrared radiation is more easily absorbed by the atmosphere. And whereas it's, for example, reflected at the ice caps by the snow cover, if it was more infrared, that would get trapped. So it would create a general planetary warming effect. And then there's what I call interplanetary hothouse effect, which is due to that effect of the spectral change. And the other thing is that it would aggravate the sun. The presence of this dust and dust falling into the sun would cause it to start to increase its amount of flaring, solar flaring. And I am proposing that the sun would evolve into a T Tauri star. These are stars that about the same mass as the sun, but they're inside of a nebula. And they are like continually flaring. They have a high luminosity in UV and X-ray. It's possible that our sun would mimic the same effects during a cosmic dust invasion. We do see effects where solar flares have been triggered after a comet enters into the sun. So it's very possible. Then this, if it goes into a T Tauri state, which I believe happened during the one that happened at the end of the Ice Age, could cause killer solar flares. So I've almost been talking an hour. I better speed up here. So it caused rapid ice melting, and this is from the coronal mass ejections onto the surface of the Earth, could cause the ice sheet to melt, form ponding of lakes on the surface, which could discharge and form giant avalanches of water, which I call a glacier wave, which could sweep down the ice sheet and cause continental geological effects. Here is the cosmic ray graph from the Earth's ice core record, from the Vostok record. And you see that was, here's the one at the end, but there was a very big one 40,000 years ago I was mentioning earlier. But you see every so often you have quite large events. And there was a Fourier analysis done of these peaks to see how frequently they're spaced. And they found that certain cycles emerged. One approaches the orbital precessional cycle of the Earth, and it's about half a precessional cycle. And then there's this one at 5,700, which is interesting because it comes close to the Mayan cycle duration. So there was a minor superwave event at 3,300 BC. That was this one during the last ice interglacial. Here we are in the interglacial. But it was a brief one of no more than 100 years or so. So this is the one 15,900 years ago that is the one that comes out of the zodiac star lore dating. And here's from the Antarctic ice core, bird ice core. And you see at that date, there was a very large ionization spike in the ice. And they found a lot of chlorine and fluorine ion in the ice. And I've written a paper about this. They find it's modulated, or I found it was modulated with the solar cycle. And I believe this is stuff that was brought into the solar system, and its entry into the solar system was affected by the cycle of the sun. So this lasted about 100 years, and you see every 11 years or so there's a variation of the amount. This is a depiction of how that stuff would look in the solar system around the Earth. I tested my theory by doing neutron activation analysis of samples of dust filtered from the Greenland ice core. And at that time was Camp Century ice core. It was the only one that was in existence at that time. And I reasoned that if I found high levels of iridium, now this is beryllium-10, that's another study, but this is my study here. I reasoned if I found that iridium had increased, this would be a good test of the hypothesis. It would indicate that there had been an increased amount of cosmic dust at that time. And sure enough, I found 2 orders of magnitude or more increase of the iridium. I also found nickel that increased, and these were iridium and nickel were in cosmic dust proportions ratios. And this sample had the most iridium, and it was a very unusual sample. It also had tin and lead in it. Here's me with the gamma ray counter back in 1981. So this was my main verification of the theory was based on the ice core, besides all the evidence on galactic astronomy I presented. And took me 30 years to publish this paper on the tin and lead material in there, because a lot of astronomers wouldn't publish. They said, they were claiming, oh, you got contamination in your ice core samples. And I told them, well, they were filtered by a fellow, I didn't filter them. This particular sample was filtered by Lonnie Thompson, who was given the presidential award for his cleanliness. And he used a clean room with triple distilled water. There's no way that this was contamination. And here, finally, I did all sorts of studies of this. I got the insight to test the isotopic ratios, and we found 3 isotopic anomalies in 3 of the 10 isotopes that were significant. And it was the first time an isotopic anomaly had been discovered for tin. So that was definite evidence that they were of cosmic origin. Anytime you find an isotopic anomaly, that indicates cosmic origin. The other is the micrographs I made at RPI. And you see, this is also a tin particle. They're mostly tin, but they have a little lead. And the tin and lead is not in the solar system ratio. It's in the interstellar ratio, which indicates that this is interstellar dust. As far as I know, is the first time anyone had proven the evidence for interstellar dust in the Earth's ice core. This is what in cosmic dust studies you would call a porous aggregate. It's made up of nanoparticles that have agglomerated together, formed a larger particle. It measures about 40 or 50 microns in length here. By the way, this is a monomineralic grain here. This one that I photographed ended up being 120 microns long, and it holds the record, the world's record on size of a monomineralic cosmic dust particle. There's only one other that had been found, but it was a agglomeration of different particles. But this is all tin with some lead. And finally, I figured out why would the sample be like 90% tin and lead. And I realized that both tin and lead are superconducting below 3 degrees Kelvin or around 3 degrees Kelvin. So that means that they would have been subject to the Meissner effect. So any magnetic fields propagating through space would have sort of swept them up and concentrated them. And so all of this evidence together, finally the paper was published 30 years late, but finally got published, and it's available on my website if you want to read it. This is what a T-Tauri star would look like. And in fact, found, this is from my dissertation, NASA did a study where they charted solar flare tracks in micrometeorite craters found on moon rocks. And they made a graph of the time based on the cratering on the moon rock. They were able to get a time scale. And it seems that 16,000 years ago was 50-fold greater, the amount from what it is today. And this could have been pushed forward to a more recent date. If you figure that cosmic dust there was greater cratering at that time, so that would have compressed the scale in this area. So we had a mass extinction at around 12,900 years ago, where all the large animals in North America became extinct. And it was the biggest since the dinosaurs. This shows the species disappearance rate. And this here is the Pleistocene extinction. This is the last 65 million years. This shows, again, the mammalian death rate. It peaks out. And this is where it's the boundary between the Alarod and the Younger Dryas. And you had very high solar flare activity in this period. You also had a lot of meltwater discharge, coincident. So I believe the mammalia became extinct due to a solar flare event, super solar flare event. And I wrote a paper on this. It appeared in Radiocarbon Journal and showed the evidence. I'll present to you a little of the evidence. But this is a basic idea. Here's the sun. And spewing out one of the NASA simulations. Coronal mass ejection hitting the Earth. Now, if it's a low intensity event, we wouldn't have too much to worry about. But if it's a very powerful event, it can actually affect the geomagnetic field and decrease the field and cause it to actually impact the surface of the Earth. Now, this is a graph of from the Cariaco Basin C14 record. This shows C14 excess, radiocarbon excess. And you can chart solar cosmic ray activity by this excess. And you see that here's where the Younger Dryas began. This is the climate graph. Climate was cooling during this period. And that's in step with the increase of the cosmic ray, solar cosmic ray activity was increasing as climate was cooling, and that's doing that cloud cover effect, I believe. And right here is where you have this evidence of a solar flare event, very large solar flare event. So it didn't occur at the boundary. It occurred about 120 years into the Younger Dryas, which, different from the comet impact theory. Comet impact theory said that the cooling and everything was due to a comet impact, and it's easily disproven, let me say that. Now here you'll notice that there are these spurts in the cosmic ray axis. It turns out that these are subdivisions of the solar cycle. So that's like a fingerprint that this is due to the sun's activity. And here was the date of the main event, 12,887 years B2K, almost 12,900 years ago. So if you add, well, we're 21, yeah, almost exactly 12,900 years ago. And here's the signature in the ice record. So the ice record records all this stuff. It's like a form of astronomy. Do I see some people with closed eyes there? Wake up. Okay. Because we're getting to some interesting stuff here. So this shows, this is an electrical conductivity graph. And when the Earth was hit with the solar cosmic rays, it ionized the atmosphere and produced these ions, which were trapped in the snow. and form this conductivity spike, cyan spike. And this is the biggest spike of the entire Younger Driss. So this was quite a big event. And if you compare to the Carrington event, and here's the 1956 solar flare, Carrington event, here's the mass extinction spike. And in my paper, I did calculations and I show that it was above the lethal levels in terms of radiation hazard. It was, in terms of sieverts, it was definitely a killer event. This is, here I'm plotting nitrate. This is from ice core studies. You see that nitrate actually decreased at the time of this spike. So it took me a little while to figure that out. And I realized that nitrates in snows are destroyed by UV. And this would have produced a lot of UV radiation. And that's why you get a dip in the nitrate curves. You see ammonia for later on and a lot of dust. This is dust material that's from studies of passing a laser through the ice core. They see how much dust is in it. And so this is evidence of biomass burning. And so you see that this event was associated with triggering wildfires. And you actually see a horizon here, carbonized horizon at Uccello in the Netherlands. And it's evident also in North America. There's in the far west, they found a carbonized layer. And I believe that there have been also these glacier waves like coming from the ice sheets that could have also buried the mammals, could explain the frozen mammal remains in Alaska and Siberia. That this water was not ocean water that asphyxiated them. It was glacial water, cold glacial water, avalanche size. It might have been about 500-foot high wave coming down. Here's where what the ice sheets look like at the end of the ice age. So the North American ice sheet, European ice sheet. And if you chart altitude of the ice sheet versus distance, it looks about like this. So if a wave got started up here, what that noise is, it would trigger other lakes to empty and it would grow in size, sort of like a domino effect. I did publish this in a paper some years ago. It's also available on my website. So by the time the wave gets to the edge of the ice sheet, it's going about, hundreds of miles an hour figure, and it could be 500 feet high or more. And since it came from an altitude of 2.5 kilometers in the center of the ice sheet, it would be able to mount mountains, it would actually sweep over mountains and could go over the continent. And that's why I call it a continental glacier wave. And even into the ocean. So it would have gone across the ice shelf that was there at that time and dumped debris out in the middle of the ocean. And these are what we call the Heinrich events. And Heinrich was proposing that this material was transported from the continents out into the middle of the ocean, Atlantic Ocean, by icebergs. That was the only thing he could think of. But the problem with the iceberg theory is it should have been deposited gradually as the iceberg melted. And instead they find it was deposited so suddenly it actually compacts the biomaterial on the below it. So all this I discussed in that paper on the glacier waves.
Paul,
By the way,
Paul, I'm sorry to interrupt. I just wanted to remind you of the time. We'll probably need to wrap it up fairly soon.
Okay, I'll wrap it up. And here the Grand Canyon. This is Scablands Canyon, Columbia Gorge. All these could have been carved out by this. These glacier waves would have brought water down. This would have been a whole lake here that over millions of years, it would have drained through existing crevice and would have kept enlarging until we got the Grand Canyon. And this just shows the event at 40,000 was quite a whopper. This is the carbon-14 increase. It was huge. And it was actually strong enough to defeat the Earth's magnetic field. It creates a ring current, which cancels out the Earth's field. And here's evidence they found that it's called the Lachamp excursion occurred at that time. And for 400 years or more, the Earth's field was at 5% intensity. And that's when you see the extinction of the Neanderthal, that they found that all the Neanderthals died out at that time. And this occurred at the time of the cosmic ray event there. This is cosmic rays, Brilliant 10. It's 5,300 years event, and we've had some smaller events, but only maybe year-long events. Do you want me to wrap it up now, or should I go into Dunov, the prophecy that he said he believed that there would be one coming in year 2029?
Well, I think we probably need to wrap it up now and give people
Okay.
a chance for some questions.
Right.
It's been
Okay.
a fascinating talk. And thank you very much indeed for spending the time with us.